Hi there. This is one of first of our 4 videos we're going to do with talking about radical expressions for this module. So this first objective is going to be about simplifying radical expressions, and it states this: an expression that contains a radical sign is a radical expression. There are many different kinds of radical expressions, but in this course we are only going to study radical expressions that contain square roots. That means later on in Algebra 2 you're going to have problems that might look like something with a higher index. So you might have something with an x cubed in there or something to that effect. So that's what we're going to end up doing. So I'm going to hide that, delete that, because you weren't really going to need to see that. Alright, so underneath this slide we're going to have some examples of some problems here of what a radical expression is going to look like. You might have a square root of 14, or a square root of L squared plus W squared, or a square root of 2GD, or a square root of D divided by 4, or 5 times the square root of 2, or the square root of 18. Now, some of these you'll be able to simplify, some of these you won't be able to simplify. So, as an example, in a rule set here, the expression underneath a radical sign is the radicand. So everything underneath that square root sign is called the radicand. A radicand may contain numbers, variables, or both. It may contain one term or more than one term. Remember, always pause if you need to during this video, but do not skip ahead and just fast forward through everything. So make sure you watch the rest of this. Alright, so if you've already unpaused it or are ready to move on, let's go on to the next slide. The first thing we'll talk about is the simplest form of a square root expression. There's a couple of things that you'll have to remember to how do I know if it's in simplest form. The radicand has no perfect square factors other than 1. In other words, you're not going to have a square root of 9 hiding inside of there. And you'll see some examples of that later. The radicand has no fractions. You'll have to learn to deal with that. And there are no square roots in any denominator. That part actually becomes important in the third video of this one of the series when we start multiplying and dividing with radicals. We'll get to that later. Alright, so here's some examples of stuff we're going to work on. Let's start with this very first one. You have the square root of 2 divided by the square root of 50. Well, the first thing we got to deal with is the fact that, wait a minute, there's this radical here. There's a couple ways you can deal with this, but probably the easiest one is to recognize, wait a minute, 2 divided by 50 reduces to 1 over 25. From there, we'll be able to split each part up into doing the square root of 1 divided by the square root of 25. That becomes a property we'll learn about later. The square root of 1 is 1. The square root of 25 is 5. So your answer is 1/5. Now if you remember from before, when we talked about square roots, every time you do a square root, you're technically supposed to get 2 solutions for this. And that still holds true, because there's 2 ways to get a positive 1 over 25. Positive 1/5 and negative 1/5. However, for this exercise, and what we're going to do for now, if this says just the square root of something, it's positive. If I put the minus sign or a negative sign out front of it, then I'm asking for the negative, which means I'm asking for the negative 1/5. So you're not really going to get 2 answers for this. What about a problem that looks like this for the second problem there? Alright. This one is a little bit harder to do. You're going to have to do a little bit of more work, I mean. So like say the 8 squared and the 15 squared. Well, let's start combining this stuff. Well, 8 squared is 64. 15 squared, if you need a calculator, we should be using that kind of thing. 15 squared in this problem is 225. Now if I add the things inside the radical, so in other words, take the 225, add a 64 to it, I get 289. Now, I'm going to see if this can actually do a square root of 289. Second, the square root, and we have 289. And we have an answer of exactly 17. And we're not going to do pluses or minuses for a while, okay? So right now it's just positive square root of 17 because it did not have a negative sign out on front of it. This third one, oh, this has a polynomial inside of there. How would you go about doing this? Well, since you have a polynomial, we're going to actually factor this trinomial. So factor trinomial. In this factoring of this trinomial, you do however you would want to do it. 1 times 9 is 9. Two numbers that give me -6 that multiply to a 9, -3, -3. So you can factor this trinomial by doing the factor by grouping method or any other method that you've learned. I'm going to factor this out by the factor by grouping method. And then we would have this. The greatest common factor is x minus 3 times x minus 3. Or x, whoops, I made a mistake. Need to correct that. That should be x minus 3 because it was a -3. And we would have x minus 3 squared. If I do the square root of the x minus 3 squared, I'm going to write an answer of just x minus 3. I can leave it in parentheses or not. So there we go with that. I'm going to move my calculator over here and change the sign. So if you want to do this one, this is another problem similar to that one. The square root of 25 is 25. The square root of 12, the square of 12 squared is 144. And if I add them up, I get the square root of 169, and the square root of 169 is 13. So you're going to find out that a lot of these are going to be relatively easy. What about this next one? This is another one of those, but wait a minute. This has already been factored for you. So the square root of something squared, I'm going to cancel that out. So the answer is 3 minus x. Look how easy that one is to solve. You're going to look for problems like that, especially when you start solving radical expressions in the 4th video of this series. The product property of square roots in this problem. For any non-negative real numbers a and b, in other words, inside the radical, we're not going to have negative numbers. The square root of each number is the same thing as when you take the square root of the product. So, for example, the square root of 4 times the square root of 25 is the same thing as if I had multiplied 4 times 25 to get 100. The square root of 100 is 10. So we can also do the reverse of that. 100 could be 4 times 25. And we're going to kind of work with that here with the square root of 24 and a few other ones. And this is the algebra part of this. The square root of 24 doesn't have a pretty perfect square root, but we want to simplify that. So we want to find any perfect squares that go into 24. In this case, the square root of 4 times the square root of 6, because the square root of 4 has a pretty square root. What about 6? Doesn't have one. So what we're going to end up doing is, well, what is the square root of 4? It's 2. What about the square root of 6? Nothing else breaks down into that, so we write 2 squared root of 6. Looks just like that. What about if I have variables in there? Well, we kind of split it up. The square root of x cubed and the square root of y to the 4th. So in this problem, well, the square root of y to the 4th is kind of easy. The square root of y to the 4th is y squared. But what about x cubed? What we want to do is simplify it down as far as you can. So I'm going to tell you to do is take one of those x's out, and then the last part of that we're going to leave as an even number for an exponent, because that would mean I'd have the square root of x times the square root of x squared. Let me highlight that so you know what we're working on. We took the cubed and we made it into two different pieces, keeping one of them an even number, so we can do a square root of that here. And then we have a leftover piece, one little leftover guy left. So the square root of x squared is x. The square root of y squared is x is y squared. And we just have the square root of x. That's a perfectly good answer. Some people also have a tendency to write it like this: xy squared times the square root of x. Okay. Like I said, pause if you need to catch up. So in here, the square root of 128. Well, let's do this actually two different ways. The square root of 128, somebody's going to say, well, how about 4 times 32? Okay, that would mean you'd have the square root of 4 times the square root of 32, which means you'd have a 2 coming out of this. The thing about it is the square root of 32 actually has another perfect square hiding inside of there. Someone's going to say, well, what about if I did it with another 4, like the square root of 4 times the square root of 8? Well, that means this square root of 4 turns into a 2. So that means we'd have to drop down this 2, we'd have to drop down this 2, but wait a minute, the square root of 8 also has the square root of 4 times the square root of 2. That square root of 4 has another 2. So you have a 2 from the first, the second one, and the first one, and the last one, and then you bring down the square root of 2 and multiply it out. 2 times 2 times 2 is 8 square roots of 2. Now if you're saying to yourself, boy, that took forever to do. Yeah, you know why? Because you went with little baby square roots of a 4 going into there. If you really think about it, the square root of 64 times 2 would work a whole lot easier. You want the biggest perfect square that would fit inside of there to actually work. The square root of 64 turns into 8. There's a square root of 2 left inside of there. There it is. So you'll do a problem a whole lot faster if you start thinking big versus small perfect squares. What about 48? Okay, the square root of 48 could be 16 times 3. What about the square root of a squared? And the square root of b. The square root of 16 in this problem is just 4. Then we have a square root of 3. Then we have the square root of a squared, which turns into just the letter a. And then we have the square root of b, which, oh, that's just to the first power. That's a leftover piece, so we write that as our answer. How do we write this as a final answer then? Well, we put the things that we did square roots with, and we got answers of nice, pretty 4 and an a. So I'm going to write the 4 and the a first. Inside of one radical, we want to put everything else stuck inside of a radical. So we'd put the 3 and then the letter b. And it looks just like that. What about the next slide here? For this part here, it says this. This is kind of like doing something similar, but instead of multiplying, we're dividing. So you could actually do this, the square root of 12 divided by the square root of 27, which turns into the square root of 4 times the square root of 3, because 4 is a nice, pretty, perfect square. 27 could be square root of 9 times the square root of 3. The square root of 4 turns into 2. The square root of 9 turns into 3. But wait a minute, right here, highlighted in green, the square root of 3 divided by the square root of 3 is just 1. So our answer actually simplifies to something pretty 2/3. If you really wanted to, though, the smart people, like, wait a minute, this could have reduced already because each of those numbers I could divide by 3. Which means you'd have, if I divided the 12 by 3, you get a 4. Divide the 27 by 3, you get 9. So this turns into the square root of 4 divided by the square root of 9, which still gives you 2/3. So it behooves you, nice pretty word we can use there, to actually reduce first. So think big, always try to reduce. What about this one here? That's the square root of 36 divided by the square root of x to the 4th. The square root of 36 is 6. The square root of x to the 4th is x squared. We don't go any further. We're done with the problem. All right. Last slide coming up. So let's just see who is paying attention today. This first one, well, we could do it a couple ways. Square root of m to the 3rd and the square root of 9m, which means you'd have to break this odd one up into a square root of m times the square root of m squared. And then we have the square root of 9 divided by the square root of m there. But recognize that, wait a minute, we have a single square root of m here and a single square root of m there. Those reduce to 1. What about the square root of m squared here? We'll highlight that in this case, blue. As well as the square root of 9. The square root of m squared is just m on the top. The square root of 9 is just 3 at the bottom. Or, wait a minute, you could have reduced here at the beginning, which means if I have m cubed on the top and m to the 1st at the bottom, you would basically have m squared over 9, which means you'd have the square root of m squared divided by the square root of 9, which also still gets you m divided by 3. What about this one here? This one's not going to reduce for you because there's no way to reduce 108 and 25. However, you could probably start playing with the calculator a bit. Say, all right, is there a perfect square that goes into 108? Try maybe 9. Goes in 12 times. But 12 also has a 4 into it. So I'm going to do this. 9 times that 4 divided by 36. Ooh, it goes in 3 times. So the square root of 108 is the same thing as the square root of 36 times the square root of 3. The square root of 25 is the square root of 25. Nothing's going to break down further than that. Which means you have the square root of 36, which is 6. The square root of 3 does nothing. And the square root of 25 is 5. This does not reduce. This is your final answer for that one. What about this very last problem? Okay. The square root of 9 is the square root of 9. The square root of x cubed is the square root of x squared times an x to the first divided by the square root of 16. The square root of 9 is 3. The square root of x squared is x. There's still an x left over inside the radical. I'm sorry, it's going to have to stay there. And then the square root of 16 is 4. This is your final answer. So on your worksheet that you're going to get, as well as on your quizzes or tests, you're going to find some simplifying radical expressions. See you next time when we start talking about adding and subtracting of radicals.